Let me begin. Okay, so what is a module, right? So we're actually, yes, admittedly, we're going back to chapter 10. We were already in chapter 14. But that's just the way I chose to structure the course this time, because we ended up doing field extensions in the last semester, and so it just kind of bled into 13 and chapters 13 and 14. But going back here, chapter 10, Endowment and Foote, third edition, Introduction to Module Theory. So what's the definition of a module? Here we go. Let R be a ring all right, and in here, maybe I should say, really, a RNG, because we're not assuming at the outset that R is commutative or that it has 1, right? So consider a possibly non-commutative ring, and it may not be a ring with identity. So R could be non-commutative with no identity. Possible. Then a left R module over R is a set M together with number 1 binary operation plus, right, on M. It's commutative. In other words, addition is a good notation for it because it behaves like addition, right? Well, sorry, let me state it as he states it. Binary operation plus on M such that M is a Abelian group. So that says what? That says that M has 0, it's closed under negation, and the addition is commutative. 2, there's an action of R on M. Right, so in here, so what we mean is it's a mapping from R cross M to M again. In particular, the pair R comma M little m maps to just Rm. So we're going to use juxtaposition to denote that action. All right, and this action satisfies a couple rules. First of all, R plus S on acting on M is R acting on M plus S acting on M. So you have that distribution rule. You also have sort of an associativity kind of thing. RSM is, well, RS acting on M is the same as R acting on S acting on M. And you also have distribution with respect to the addition in the module. So in the sense that R, so sometimes we refer to this set as the module. Okay, so we do the same thing with group theory. Mm-hmm. We'll say the group is, it's the group of group of real number, non-zero. Yeah, I'm trying to think of as a set that has 2 different group operations on it. Nothing comes to mind at the moment, but you have a given set where different group operations are allowed. It's easier if you don't talk about a whole set, you talk about a subset, right? Like real numbers on the one hand are together, altogether, an additive group, right? But on the other hand, if you just look at positive real numbers, they form a multiplicative group. So if you have, the set of positive real numbers, you could talk about two different group operations on them. You can either talk about addition, or you could talk about multiplication. Of course, positive real numbers don't form a group under addition because they're not closed under negation, among other things. Zero's not in there. So in the same sense, when we talk about a module, sometimes we refer to the set M as the module. But the truth is, it's M paired with this module action, the action of R on M, like this. So but nevertheless, that abusive language we make, we call M the module. So we have distributivity with respect to the addition in the ring, distributivity with respect to addition in the module. And there's more. If R has a unity, right? If it has a multiplicative identity, then what else do we insist? We insist that we have one additional axiom, D. What do you think 1 times M should be equal to? M, right. And of course, all of these hold for what? For all, for all R and S, or for all M and N, right? So does this remind you of anything?
Yeah, the thing from last class, or not? Yeah, well, not last class, but I mean last semester.
Uh-huh.
Ideals.
Reminds you of ideal? Ah.
And this might be because we're using a lot of similar notation.
Yeah, I think there's similarity with ideals, formula-wise for sure. How about this? What other? Let me see here. Let's look at it as an example then for a second here. How about this? If we let R equal to, let's say, the real numbers, right? And we let M equal to, say, Rn, right? So is Rn an abelian group?
I would hope so.
So it's an abelian group with respect to vector addition,
Mm-hmm.
right? So Rn, you can add vectors together, you still get a vector. Zero vector is the zero for the space. Yeah, I mean, this is an abelian group with respect to vector addition. Is this a ring? Sure. And how are we going to define the action of R on Rn? How about this? C times x1, x2, xn, cx1, cx2, cxn, right? This is what? This is what we call scalar multiplication, right? So apparently, Rn is an R module. But if you really think about that example, you realize that you could just as well replace R with any field, right?
Yeah.
We could let R be any field, right? And we could let M be a vector space over that field, right? And a vector space over the field F is going to be an F module. So, as Dummet-Foot says on page 337, modules over a field F and vector spaces over a field F are the same. It's a good way to say it. Modules over F, a field, same as vector spaces. Over the field. Because what is a vector space? A vector space is a set where you can add vectors. There's a zero vector. The addition is commutative. It's closed under negation. In other words, with respect to a vector addition, a vector space is an abelian group. And then we also have scalar multiplication on a vector space, right? But the axioms for the scalar multiplication are exactly the same as point 2 in this definition. You have distribution with respect to addition of scalars, and you have this kind of mixed associativity idea with the scalar multiplication and vector, multiplication of scalars versus scalar multiplication. They interact in this way. And of course, also distribution across vector addition. So what's the difference then between a module and a vector space then? If they're the same, are they? Well, they're not generally the same. The difference is, the difference between a module and a vector space, in one part of it is that in a module, the scalars could be coming from a ring. So that's another way I often think of a module is, and this is sort of an intuition for it, is module is vector space where the scalars are from a ring rather than a field. Now that doesn't quite do it justice, does it? Because you notice that in general the scalars could be even non-commutative. So is that really? Yeah. And not to mention, like, the definition of vector space does not have the generality to make that sentence logical. Yeah. So that's just that's a heuristic, okay? That's a heuristic. Now, definition. Let R be a ring and M an R module. And R submodule of M is a subgroup N of M, which is closed under the action of ring elements. Meaning that, what do I mean by that? I just mean that Rn is an element of N for all R in R and N in N. All right, so submodules, of course, submodules of vector spaces are subspaces, right? But this is the generalization of the concept of a subspace to a module. There are two obvious submodules. So a silly example, right? Silly examples. You could have M equal to just nothing. M equal to, listen to me, M. I want to say what N is. N as in nanu. So you could have N equal to 0, or you could have N equals to M. Those are both subgroups of an abelian group M. Either zero group or the whole group, they're subgroups, and they're going to be closed, right? One of the things you can prove is that 0, anything times the 0 vector is 0 again. Maybe we should do that. Can you see that? R times the 0 vector. Why should that be 0 again?
Because, yeah, like we've already defined distribution,
Mm-hmm.
and so if every term's 0, just make it every term.
I don't have anything about every term here, though.
Well, yeah, like why is R times the 0 vector 0?
Yeah. I mean, this is a completely arbitrary module. What do we know about 0? You said
0 is the multiplicative identity.
Now you said no, additive identity, but you said 0. You said something about distribution. I think that's key.
Yeah.
The question is what makes 0 0, right? 0 is 0 because 0 is equal to 0 plus 0, right?
Yeah.
So you could rewrite this as 0 plus 0. Then we can use your distribution idea, right? Distributive, this is R0 plus R0, right? And then you can subtract R times 0 from both sides, right? I don't know why I'm putting these parentheses in. I don't need, why did I put parentheses? I don't know what's wrong with me. I don't need parentheses there. I don't need, I always get carried away with my parentheses, my bad. Oh well, they're almost gone. The point is, subtract R0 from both sides, what do you got? You've got...
R0 is equal to R0.
No, if you subtract...
Oh, you go to 0, yeah.
Because R0 minus R0 is 0 itself,
Yeah.
because it's the additive, basically using the cancellation property in...
Yeah.
however you want to couch it in terms of basic group theory, but there it is. So that is not an axiom, but it is a pretty near consequence, an almost immediate consequence of these axioms. And that's also how you prove that a scalar times a 0 vector is 0 in a vector space. Same argument. So, yeah, that's one thing I can say about module theory is getting better at module theory is getting better at vector space theory. They're this is actually a little bit harder than vector space, right? Because we don't have necessarily division of our scalars when they're non-zero. So, yeah. So these are the trivial submodule, and this is an improper submodule. Like proper submodules were when you have n is not equal to m. So, all right, so let's see here. So some examples then. Examples from Dummett and Foote, page 338. Example 1, he has let R be any ring. And then M equals to R gives module. All right. See, because what's the multiplication? What's the module action? How are you going to define? How do you define R times M here? It's just the multiplication in the ring.
Yeah.
So it's just multiplication in the ring, And that satisfies all these rules. So, yeah. Going back to vector spaces again, this is the statement that any field is a vector space over itself. The real numbers are a real vector space. The complex numbers are a complex vector space. Z mod a prime is a Z mod P, is a vector space over Z mod P. So there you go. Still that silly comment, it generalizes to modules. Example 2. All right. Example 2, he has are a field. All right. And so I bet his next example is going to be M equals to n tuples over the field. Right? So this is of the form x1, x2, xn, such that, you know, xi is in F. So it's easy to check that I don't know why he's calling it a fine n space over F. That's what he calls it anyway. He calls this a fine n space over F. I mean, it's his baby. It's their baby. They get to name it. So a fine n space. I guess in fairness to them, I don't really have a name for it. I just call it Fn. So hey, I got a name for it now. A fine n space. There we go. So you know it's not ugly.
I was going to say anything.
It's too risky for YouTube. You don't want me to fat shame my space? Something? No? All right, sorry. Sadness. Okay, so anyway, yet another example of a module, right? And how would we define, so that's definitely addition of vectors, the usual addition of vectors, instead of the zero vector, negatives, great. Scalar multiplication, defined the same way as we did over Rn, right? Okay. There's another example of a module. But honestly, I don't know why he did that. I would have done Rn. See, because maybe that's his next example. 3. Ah, what do you know? Yes. See, I would have skipped straight to example 3 if I'd been more on my game. So, again, for any ring, let M equal to Rn, which of course is n tuples of ring elements. So it's, again, an additive abelian group. It's redundant. It's an abelian group with respect to vector addition, just like before. And you know, I can define x plus y. The ith element of that is, by definition, xi plus yi. And r times x, the ith component of that, is r times xi. So this defines of addition and r multiplication of M. So we can, you know, we can define operations on vectors by saying this is the rule for the ith component, right? And this for all I. That gives me a definition, which is just a formula to say that you scalar multiply component-wise, and you, you know, add component-wise. And again, I'm abusing language a bit there. It's not scalar multiplication here. It is what? It's our module action. But I would understand that as being in a scalar multiplication where your scalars are from a ring. That's how I think of it. Okay, so that's that. This has a name. This guy right here is known as the free module of rank n over R. It's a free module because you're looking at n tuples over the ring. There's no conditions on it at all. They're completely free. Okay. All right. So he points out that there are, well, he says, we'll shortly see that free modules have the same universal property, quote unquote, in the context of our modules that free groups were seen to have in section 6.3, which we have not covered. So there's a shout out to a chapter we haven't covered in Dumb and Foot yet. Sorry about that. And the obvious submodule of Rn is given by the ith component. So he's like, here's a submodule. You can just let n equal to, you know, 0, xi, things like this. So that gives you a submodule. Because if you add two things of that form, they're still of that form, right? Zero's in there. If you do multiplication, the R action, what happens? 0R, RXI, 0R, but we just proved 0R is 0 for a ring. I mean, anyway, this is a ring multiplication, so it's 0, RXI, 0. The point is it's an element of n again, right? So it's closed under the R module action, and it's a subgroup. It's a submodule. Hooray. Of course, there are many other submodules of the free module, but those are some example ones. 4. This is fourth example here. He says the same abelian group may have the structure of an R module for a number of different rings R, and each of these module structures carries useful information. Okay, so he says specifically if M is an R module, all right, and furthermore, S is a subring, of R, all right? With 1 in the subring equal to 1 in the ring. So we're assuming that is an R module for a ring with identity. Right. And remember the fussy thing, if you don't insist on identities for your subrings, you can have a ring with an identity with a subring which does not contain the identity. There's funky stuff that goes on there if you start looking at the theory of rings without identity. So we're assuming it's not the weird stuff, like the subring has the identity of the ring in it, all right? That's the context here. And then M is automatically an S module as well. Is naturally an S module. So here's a good example of that. If we have M equals to R module, that means we could also look at M is a, actually, let's make that just an R module, is a Z module. Maybe let's see, what do I need for Z to be a subgroup of M? Well, I guess that's not obvious. I didn't say R was infinite here, did I? So let me scale it back here. I'll go back to R. But anyway, anything of characteristic 0 has what? Any ring with characteristic 0 has a subring of the integers in it.
Yes.
Because you can build the integers from 1. So anything, that's an R module is a Z module. And if you, on the flip side of things, if you had a characteristic N ring, then anything that's like, and then it would be a Z mod N module, because you could build one with one. You could build Z mod N if the characteristic of the ring is N. But you have that. But anyway, what he says is in the book, he says the field R is an R module, a Q module, and a Z module. So he just takes the case. I was saying M equals to an R module, but he's taking the case M equals to R, right? It's like M equals to R it's an R module, first of all. It's also a Q module. And we can also look at it as a Z module. That one set is all three of these different kinds of modules. So, all right, example 5. We haven't really gotten to anything that makes for scary homework problems yet, have we? No. Not too bad so far. Don't worry, all of a sudden it'll happen. So 5, if M is an R module, and for some two-sided ideal I of R, huh. Well, let me look at it this way. I thought, I'm confused, Audric, because we talked about ideals before, right? But we talked about it in the context of commutative rings. Yeah. And so we didn't talk about two-sided ideals. Like for us, ideal just meant that it was is a subset, right? Like I is a subset of R, right? And Ri is a subset of R, basically, for all R and R. So I call that Uber closure. Yeah. So I had to be an additive subgroup of the ring such that it was closed under multiplication by the ring. And not subset of R, but subset of I. Duh. So we did that, but we could just as well have written IR is a subset of I, because we were looking at commutative rings, right? For non-commutative rings, those are in equivalent conditions. And so a two-sided ideal would be one for which you have both left and right closure of the ring multiplication.
Without it being commutative?
Yeah, if the ring multiplication is not commutative, two-sided ideal would be one like that happens. And then he says something. So he says, Oh, okay, I'm just missing it. So what's the words? Okay, so if M is an R module, and for sim, I'm not, I was parsing the sentence wrong, and it was confusing me. So he's like, M is an R module, and for some two-sided ideal of R, right? We have, all right, here it goes. Keep losing my place. AM equals to 0 for all A in this two-sided ideal and M in your R module. All right, then what? So that's the setup, right? Well, this you can then use to create a corresponding. So here our last example was talking about, given a module, you have subrings, you can form submodules with respect to the subrings, right? So now the next step is to say, oh, well, if you've got a module and the module action behaves well with respect to a two-sided ideal in this sense, if it annihilates this two-sided ideal, this condition here, I would say, this condition is that module is annihilated by I. Right? Then you can set up the M as a R mod I module. Now, if you remember, we talked about how the definition of the factor ring only made sense if it was an ideal, right? In the non-commutative case, for the factor ring to make sense, you needed a two-sided ideal. So that those things can be, oh, I guess I can get rid of this now. And so what's the rule? We do R plus I is a typical thing so this is a typical element of the factor ring, R by I, right? Multiply that by M, what's the rule?
Oh, we have distributed. Oh wait, no, but it's like it's like the.
I need an element of M.
Yeah.
So how do I get an element of M from this?
You multiply by the identity ring in the ideal.
Well,
The ideal.
yeah, this is the ideal. It's not the identity.
Yeah.
I mean, the identity in this, if R is for a second here, suppose R is a commutative ring with identity, then the identity in the factor ring is 1 plus I.
Yeah.
Now, we know that this has to be equal to M.
So doesn't MR equal 0 by what we said above?
No, MA,
Oh.
AM is equal to 0.
Okay. So MR would be MR for M and M, right?
Yeah, just RM, but yeah, you got to write in that order. But yeah, because we have to remember we don't know, we don't have a definition for MR.
Yeah. Oh yeah, because it's
Left.
one side of ring. Yeah.
It is a left R module, which means R has to be on the left in the expressions.
Okay.
However, as you might be not surprised to learn, there's also right R modules, which then MR will be defined for. But we're doing everything left-handed. We're inspired by the Princess Bride. Let's see here. So later in this lecture, I will announce that I'm not left-handed, which is actually true.
Isn't your brother left-handed?
He is, because he's evil. All right.
That was kind of crazy.
So if so, continuing with this discussion just a little bit, if R is commutative, so R commutative with 1 and I maximal, what is this R mod I module? What's R mod a maximal ideal? Fill in the blank. Thus, M is a blank space.
Is it a field?
Yep.
And then for it's a vector space?
Correct. Remember, ring mod maximal ideal gives us a field. So, yeah. So anyway, this is yet another construction of a new module from an old one, if you've got this annihilation going on, right? All right, so he says the next example is of sufficient importance to be singled out. And so this is, he said, it will form the basis for our proof of the fundamental theorem of finitely generated abelian groups in chapter 12. Don't worry, we'll get back to chapter 12. So we will not cover all of Dummett and Foote, mind you, as you have other things to do in your life, as do I. But we'll get a good chunk of it. So here's Z modules, example. What can we say about Z modules? He says let R equals to Z, right? Then, and A, any abelian group. We can make A into a Z module as follows. So how are we going to define n times A? Actually, we've already done this in group theory, right? So NA is what? A plus A plus A n-fold times, right? Or it's 0, or it's minus A, minus A, minus A, minus A n-fold times, right? Well, so this is n times. This is minus n times, technically. So we're looking at 3 cases, n greater than 0, n equals to 0, and less than 0. So all I'm telling you is that we define n times A in an abelian group by either repeated addition, by 0, or by repeated subtraction of the element for any integer n, right? And so, indeed, that makes A into a Z module. Every abelian group is a Z module. And as he says, Z modules are the same as abelian groups. Why is that?
Because they're groups that are commutative, essentially.
Yeah, so I mean, we just started with, an abelian group, right? And we produced, I claim we produced a Z module with using the abelian group, right? Here's the module action. How do you start with a Z module and get an abelian group?
You have Z is at work done by an action.
No, it's easier than that. What was our definition of module?
A module is it's an additive group.
Like number, yeah, it's an additive group. It's, in fact, we said a module is?
An additive group acting on a set.
We said it was a abelian group.
Abelian group, specific.
So it's part of our, it's part of the definition. Like the converse to this argument is stupid. It's assumed that a module is an abelian group. So, yeah. Yeah, it's easier than that, so it's easy. Now, he says it's immediate that Z submodules are the same as subgroups. Subgroups of a Abelian group, right? All right. Now, he says, if A is an abelian group containing an element x of order n, then n times x is equal to 0. Thus, in contrast to vector spaces, a Z module may have non-zero elements of x such that nx equals to 0 for some non-zero ring element n. Right. So he says, in particular, if A has order m, then Lagrange's theorem says mx equals to 0 for all x in A. Note that A is a module over M. Note that then A is a module over Z mod MZ. Let's see here. If A has order M. Example. Let me write out. So you have an abelian group, right? Order of A equals to M, right? So if the order, remember that any element of the group raised to the order of the group power is the identity. In additive notation, that becomes any element of the group added to itself m-fold times is 0, right? So if x is an element of A, then x plus x m-fold times is equal to 0, right? Or in other words, mx is equal to 0.
Yeah.
And if mx is equal to 0, then m times then mkx is also equal to 0, right? In other words, phooey. Well, that's unfortunate. I've used M for module element. Here I'm using it for order of the group, and that notation is interfering with my mind. I mean, I understand it, but it's messing with my presentation. Anyway, let me stick away from that. So the point is, let me not try to exposit this further because I'm just getting into notational quagmire. The point of this is that, in fact, if you look at anything, if you let, I don't know what to say, J be an element of any multiple M of the integers, then certainly Jx is equal to 0 for all x in A, right? In other words, if we look at I equal to mz, it annihilates A, right? Under the natural Z module action. That means that we can do what? We can view A as a what? We can also view A as A is Z mod MZ, aka ZM module, where we define the module action by what? X plus MZ acting on, not X, I shouldn't use X here. Blarg, J plus MZ, I shouldn't use J either, son of a gun. Any other letter, I don't know. Q, there, that's weird enough. Q plus MZ acting on typical element of my abelian group, which I've been calling X here, is just equal to qx, yeah? But indeed, an abelian group of order m is naturally a z mod mz module. Right? But I think the more interesting thing here is just for a module action, we can have m non-zero acting on x, which doesn't also have to be 0, and it gets 0 again.
Yeah.
This is in vast contrast to like vector spaces. In vector spaces, if you have a scalar times a vector equal to 0, there's a theorem that says that either the scalar or the vector or both have to be 0. It's inescapable.
Yeah, well, that's because they don't have, it's not it's a field.
Right. It's a field, and the vector space sort of interacts with that field.
Yeah.
It is because it's a field, right? That's it. Let's see here. So he says, in particular, if P is a prime and you have an abelian group of prime order, then Px is equal to 0 for all x and a. That makes it a z mod pz module, which of course makes it a vector space over the field Fp. He says, for instance, the Klein-4 group is a two-dimensional vector space over F2. These groups are abelian, elementary abelian P groups, is discussed in section 4.4. All right, let us move along here. Here we go. Now here is the example. We'll be on this example for the rest of today. Because this example is how the theory of modules ties in to the study of linear operators on a vector space in a non-trivial way. And this is, well, I'm always interested in linear algebra, so to me this is the heart of the matter. But anyway, let me erase all this, yeah. Yes, we will do that. We're going to do some pretty technical linear algebra in here before the end of the semester, so don't worry, it's coming. So fx modules. Well, he says, let f be a field and x be an indeterminate. We're going to let R be polynomials in that indeterminate over the field. So what does that mean? A typical element of R is what? Like A0 plus A1x plus plus AN x to the n is an element of R. So finitely many, every element of R has finitely many non-zero terms. You can't have infinitely many. But there's also no top on the order of n. N can go as high as you want. So R is an infinite ring, even if F is a finite field. All right. And he says, let V be a vector space over F. And let T be an endomorphism of the vector space, which is just fancy linear algebra speak for let V be a linear transformation from V to V. All right. Okay. What's the module? We've already seen that V is an F module, but the linear map T will enable us to make V into an Fx module. So we already know V is an F module, right? Fine, we talked about that earlier. But in fact, we now describe how to make V into Fx module as follows. All right. So he says define. So in a moment he's going to run us through, he needs to remind us some things about the theory of operators in terms of like operator notation. So first of all, operator to the 0 power is defined to be the identity operation, right? Operator to the first power is the operator again, right? Operator squared is the composite of the operator with itself. Operator cubed is the operator composed of the operator composed of the operator, but that gets kind of hard to write. So instead we'll just say, well, it's t composed with t squared, isn't it? Or you could look at it as t squared composed with t. I mean, I don't know which is more convenient to us, but whichever way you want to go, yeah? And so forth, the nth power of the operator is equal to, t composed with t to the n minus 1, right? Or you could write it as t to the n minus 1 composed with t. I can't make up my mind. The operator commutes with itself, so that's nice. This is how we define operator powers, okay? So how are we going to let fx operate on the vector space? Okay, let me write it down. See if you can guess it without looking at the book. Have you already looked at the book?
No, I have not.
Okay, good. So let's talk about it. We want to let, what's a typical polynomial? Like a0 plus a1x, an x to the n. We want to let that polynomial act on the vector v, right? So this is a typical thing from my ring. So this is from the ring, and that's in my typical vector. It's too ugly. I'm going to erase that anyway. Too hideous. And it's got something to do with this t thing. So what am I going to do?
Okay. T is a linear transformation.
Mm-hmm.
B to B.
Right. So that means, for example, that means t of v is an element of v, right?
And this is F. This is a thing. This is a thing in R actually acting on B.
Mm-hmm. We need to get back a vector again.
So
because we're looking at
for me it'd be like A not B.
A not v.
Plus A1x B.
Well, but that won't necessarily be in the A not v. Yeah.
A not B.
Well, would that be in plus A1v? So you're just going to change all the x's to, you're just going to put A1v plus da-da-da plus ANV? Huh. Well, Huh.